Good morning, everybody. This is Mr. Steele. I'm obviously not here, or if it's not obvious, you probably want to look around a little bit and check your surroundings, make sure you know where you are. Anyway, I'm on a field trip today, probably in Nevada right at this time as you're sitting in class, but of course don't want you to fall behind and want to be able to get through this lesson on geometric sequences today. So, as you'd expect, I'm going to go through this just like I did the last time, go through what a geometric sequence is, talk about how we can write the rule, how we can recognize the pattern as well. That would be classified as geometric, and then use that information to write the rule and find terms. Just like we did with arithmetic, basically everything's the same here, just with a new kind of pattern and a new kind of rule that's going to match that. So, to kind of start things off, you can probably anticipate where we're going with this, because if we started talking about patterns where addition and subtraction were the focus, you can probably anticipate where we're going next. So the first thing I'm going to do is I'm just going to write out a sequence. Just a sequence, pretend we're not, nothing funny is going on here. We're just writing out a sequence, just like you would any other time. So, writing a sequence, writing it now. So, hooray, we have a sequence written out. And that sequence is 2, 6, 18, 54, 162. So you look at that and you go, okay, great. You know what? Who cares? It's a sequence. Well, you might say that anyway, but that's beside the point. So as we look at this guy, the first thing you'd probably want to do is you'd want to see, does it fit the pattern we've been using all this time? Like, could this be an arithmetic sequence maybe? I mean, maybe this is just arithmetic. And if it was, we would be able to tell because we'd be adding the same number every single time to get to the next terms. So if we notice here, if this were the arithmetic, we add 4 to get from the first term to the second term. That means we should have 6 plus 4 is 10. Oh, it's not 10. Notice this time we add 12. And this time we add 36. And this isn't this is not arithmetic. This is uncharted waters. This might be scary. But in reality we've got something different here. Like, this just means that we're not looking at an arithmetic sequence anymore. If it were arithmetic, it would have said plus 4, then it would have said plus 4, then it would have said plus 4, and then just for kicks, it would have said plus 4. It doesn't, so therefore we have something else different. Now when you look at this, what do you notice? 4 plus 4 plus 12 plus 36 plus 108. You might be thinking, oh, that's interesting. It looks like there's kind of a pattern in those differences themselves. It looks like we're going 4 times 3 is 12, times 3 is 36, times 3 is 108. Well, interesting. I mean, let's look up to here, though. Like, forget about the pattern of the differences. Who cares about those guys? Look at the pattern in our original terms. To get from 2 to 6, we multiply times 3. To get from 6 to 18, we multiply times 3. To get to 18 to 54, we multiply times 3. And although you might not know it off the top of your head, to multiply, or to get from 54 to 162, we multiply by 3. So it appears in this case, if we were to talk about the pattern in this sequence, this 2, 6, 18, 54, 162 sequence, our pattern is actually multiply by 3. And that's a distinctly different pattern than what we had before with arithmetic. Instead of adding the same thing over and over again, we are now multiplying. Or, multiplying, dividing, the same kind of thing, same way adding and subtracting went together. So as you probably anticipate from the large print title at the very top of the screen, a pattern like this is going to get a name because multiplying is a pretty common thing. I mean, otherwise you wouldn't have learned it back in 3rd grade. So in fact, that pattern is called a geometric sequence. So let's start by getting a definition down for a geometric sequence, because that's what our focus is going to be today. So a geometric sequence. Now you hear geometric, you probably think of shapes, and while that is absolutely accurate as far as what I think of when I think of geometry as well, geometric sequence does not have anything really to do with shapes, not that we see here. And the formal definition for a geometric sequence describes that pattern of multiplying over and over again in a very formal way. A geometric sequence is a sequence, you can assume that from the last word, is a sequence with a constant ratio between terms. So the last time we talked about having a constant difference or a common difference between all of the terms of the sequence. Now we're talking about a constant ratio because you multiply by something, or there's the same fraction, the same thing the ratio of the terms is always the same. So again, like usual, we start with the formal definition, and then the informal definition would be that you multiply by the same thing over and over and over again. So kind of a nice thing. I mean, not too bad. And it might seem a little bit weird here that we didn't say, multiply or divide. In reality, you'll see that we can turn any division thing into something. But as we look up here at our sequence, we can tell it's geometric because the constant ratio between terms is exactly what we see. Notice that 6 over 2 equals 18 over 6 equals 54 over 18. All of these guys, these ratios, and again, ratio is just a fancy word for fraction, all these fractions are all equal to that constant ratio of 3, which is what we are multiplying by over and over again to get the next terms of this geometric sequence. So lovely, cool. We got this pattern. We're multiplying by stuff. We're going to call it geometric. Go for it. Lovely. That's wonderful. So, okay, that's great. What do we do from here? Like, how can we write stuff about this? Like, what would the rule look like here? Because if we're not adding a whole bunch of stuff, our old arithmetic rule isn't going to do much good for us. Well, if we actually look through at this little sequence here, this 2, 6, 18, 54 thing, if we look at this guy, we can kind of anticipate what kind of sequence rule will actually work if we kind of think about how it is that we generate all the terms here. So what I'm going to do first, before we write a rule, that is going to be our first goal. We're going to write the rule, and here's the formal geometric rule, blah, 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 blah. Before we do that, I think it's kind of helpful to think about what's happening here. So for this first term, this 2, we just have 2. What do you mean just 2? Well, it's just 2. Like, it's the first term in the sequence, so we're just going to sit there. To get this 6, we take 2, and we multiply it times 3. Well, you can think about, well, why do we do that? Well, we recognize that the pattern was multiplied by 3. So, okay, 2 times 3. 18, we take that 2 times 3, and we multiply times 3 again. 54, well, that's going to be 18 times 3. So that's 2 times 3 times 3 from the 18 times another 3. And then, if you can believe it, 262 is 2 times 3 times 3 times 3. That's 54, as we saw right here. And then times 3 once again. So what do you notice is happening here with each of these terms? Yes, George, because you're usually the only person to comment and volunteer at any point. Oh, you're right, George. Yeah, I agree. Yeah, I noticed that there's more 3s every single time that we're multiplying by. So in fact, that thing should kind of anticipate what our pattern's going to look like. Because look at this. We have 2, and then how many 3s are there? 0, 0, 0, 4. No, not 4. There are 3. There are 0. There are 0 3s right here. So this is like having 2 times 3 to the 0. This one, well, there's 1 3 there, so it's like having 2 times 3 to the first. And then from here on out, you guys know how to count, so you can probably see what's happening. As we're looking at this pattern develop, we're starting at 2, just the first term times something to the 0 power, so it's just the first term, and then we're multiplying by more and more powers of 3, like 1 more each time, because again, we're just multiplying over and over again. And exponents are just multiplying over and over again. There's probably a sign right above this screen that says something about multiplying, or exponents are just multiplying over and over again. So as we go to write the rule for this particular sequence, we're going to use that fact. So for this sequence, if I want to talk about a formula to find the nth term, it's going to start with a sub n. This is saying the nth term of our sequence, and we're just calling this sequence a. That nth term is going to be given by the first term times, in this case, 3, because that's our ratio. Our common ratio is 3. And now if we want this pattern to develop of powers 0, 1, 2, 3, 4, since a sub 1 would give us n equals 1, we have to start with n minus 1 as our power. So that way when we find a sub 1, we'll have 2 times 3 to the 1 minus 1, which would be 2 times 3 to the 0. And so as you kind of look at this, you'll notice that this guy does in fact generate the terms of the sequence. Like 2 times 3 to the n minus 1 is in fact our rule for the sequence that we've looked at here. And of course, I've been throwing some terminology out here. When I talk about this constant ratio or common ratio, like the number I'm talking about in this case is that 3. That ratio is 3 because it's what we're multiplying over and over again. So we're seeing in here, we're seeing that ratio up here. It's the thing that's being raised to the power. And then also, that 2 is sitting there, too significant because it was just our first term. So both of those guys are in there. So, okay, great. We've written out a rule that makes sense for this particular sequence. But what about every other geometric sequence in the history of mankind? Like, what would they look like? Well, think about it this way. If we're going to write a rule for a geometric sequence, I'll go ahead and leave this in green too. Yep, I'll try to leave it in green. So if we're going to write a rule for a geometric sequence, according to this kind of model, if we kind of assume this works, and we can test it out later, don't worry. If we assume this is kind of our model, we need to start with the first term in the sequence. So in this case it was 2, and the reason we want to start there is because then from there we just start multiplying by that ratio over and over again. So we start with a sub 1, and then we're going to multiply times that common ratio r. So whatever that ratio happens to be. In this case r was 3, so our ratio was 3. And then whatever it is, we raise it to the power n minus 1. And that will describe to us this geometric sequence that we have. So again, what were these guys? That was our ratio. That little r is our ratio. It's the number you multiply by. So as we were talking about. And then this guy over here is your first term. So this isn't like arithmetic where we have to go back and find a sub 0. In this case, doing that would just be more work. Instead, it's easier for us if we just start with the first term sitting there, because the pattern itself develops really nicely in that way. That looks like a duck's head. There we go. Okay, so there we go. This guy. This is going to be our holy grail for today. Like this guy, this rule, this is that big thing we need. Because now that we have a rule, we're going to start by going through and trying to model out a bunch of arithmetic sequences by using this rule. Well, not a whole bunch, because again, you guys get tired as soon as anything happens. So we'll do a couple, and then we'll go through and we'll start to do some of the higher level stuff like we did before. Hey, so what we're going to start with here is we're going to begin by not actually writing the rule. I lied in the last one. What we're going to do instead is we're going to focus on just finding the common ratio, because I mean, if you think about what we just did, none of this rule would be possible without recognizing that multiplying by 3. And although it was easy to see the multiplying by 3 this time, sometimes it's not so easy. So if we want to ever have any hope of writing a rule quickly, efficiently, and correctly, we need to be able to identify that ratio, because the first term is easy to find. You just look at the list and you find the first term in it. That ratio, though, sometimes it takes a little bit more work. So for this first part, we are going to find the common ratio for each sequence. As of right now, all 3 sequences are suffering from the exact same ailment. All of them are invisible. So we're going to start by making one visible, and then we'll go through and actually find the common ratio for it. So I'm going to start with a slightly easier one, and then we'll look at some harder ones. Maybe I'll even let you try one. We'll see if you're ready for that. So here is the sequence we are going to look at first. And that's fun. My phone buzzed. So we are going to start by looking at the sequence 8, negative 24, 72, negative 216. And immediately, if you're really into arithmetic sequences, your mind might be getting very upset right now, going, "Oh, what? But the signs are changing. What? You can't do that." Well, no, you couldn't do that with arithmetic, because you couldn't add a number and then add that same number and have it change signs a whole bunch of times. But remember, we're in a new world now. We're in the geometric world, and in this geometric world, like, you're multiplying by things. So of course, our goal here, we want to find the ratio. We want to figure out what is r, and in fact, we can do that fairly quickly. In this case, just by looking at the first term and then kind of hoping and crossing our fingers that everything works nicely. So the question I'd ask you is, what do you multiply to get from 8 to negative 24? Well, 8 to 24, if you go 8 times 3, you do get to positive 24. But in order to get that negative in there, we would multiply by, it appears, negative 3. Not negative 23, that'd be a large number. So now the question is, well, what is negative 24 times negative 3? Because if negative 24 times negative 3 is equal to 72, hey, we might be onto something. Well, let's see. 24 times 3 is 24 plus 24 plus 24, which makes it 24 plus 48, which is equal to 72. So it does appear that we again multiply by -3, and if you have a calculator or if you just trust me, you can verify pretty quickly that this one is also being multiplied times -3. Therefore, it appears that our common ratio would be -3. Okay, well great, we found our answer, yay, we're done, because nobody ever really cares about doing anything or learning anything beyond that. Well, in fact, I'm going to make a point first. This -3, we got by observation. We just kind of looked at the sequence and saw it. Well, if that's not possible, we can instead look at the terms and actually build up that ratio like we did up here at the very top of our screen. Like we can actually physically form the ratios. We can ask ourselves, what is the second term? Actually, I'm going to start that way. What is the second term divided by the first term? So a sub 2 over a sub 1, that was -24 divided by 8. And then we can ask ourselves about additional terms that come on later. What is 72 divided by -24? And or what is -216 divided by 72? And each of these guys is going to give us our ratio, because there's a constant ratio between the terms of the sequence. So in this case, as soon as we answered for ourselves what was -24 divided by 8, we were able to see, oh, that's the same thing. We're multiplying by -3 because -24 divided by 8 is -3. So that gave us our ratio just as well. It confirms that r is -3. So the reason I made that emphasis, or I pointed that out right here, is that in our next example, it's not going to be quite so obvious what we're doing, because it's not always that way. So we're going to go, oh, a fraction, oh, shoot. Uncover your heads, you're not ostriches. Come on now, it's okay, it's just a fraction. How would you feel if you were a fraction? Everywhere you went, people screamed like you were Godzilla. It's not a fun life, I'll tell you that. So there we go. Here is our second geometric sequence, or allegedly geometric sequence, because we really don't know at this point whether it's geometric or not. So now I ask you, what's your ratio? And a couple of you might be able to jump on it. I mean, it's okay, it's there. The problem is, I don't think it's quite so obvious in this case. Like, you know, what do you multiply to get from here to here? Well, it looks like it's going to be a fraction, but then is it the same fraction? Not always clear. So let's do it with this kind of method. Let's look at this kind of thing and compare the different terms. So in this case, if we want to compare the second term to the first term, that means we have to do 5 over 8 divided by 1/2, and the only thing worse than a fraction is two fractions being stacked on top of each other. So remember, in reality, when we're talking about a ratio, we're just saying divide. So our question to ask ourselves is, what is 5 over 8 divided by 1/2? See, it looks a lot cleaner already. So 5/8 divided by 1/2, we know that little trick. There's a trick for that. There's something we can do. In fact, I was going to say there's an app for that, but there probably is, you know, fraction dividing app. I'm sure they have one out there. It's probably a rip-off, but, you know, okay. We get this. 5 over 8 divided by 1/2 is 5/8 times 2 over 1. We took the reciprocal of the second one and changed it to multiplying. And then finally, it looks like our ratio between those first two terms is going to be 10 over 8, which simplifies to 5 over 4. So it would appear that 5 over 4 equals r. The question is, does 5 over 4 actually equal r? Or was this just one of those mirages and things? Like, are we maybe seeing things? Let's see. If we're multiplying by that ratio, 5 over 4, 1/2 times 5 over 4 would be 1 times 5 is 5, 2 times 4 is 8. That one definitely works. Let's try it again. If we multiply 5 over 8 times 5 over 4, 5 times 5 is 25, 8 times 4 is 32. This one works too, and I'm just going to go ahead and point out that if you multiply 25 times 5 and 32 times 4, you will in fact get this guy as well. So it appears that we have in fact found our common ratio, and that common ratio is equal to 5 over 4. Hooray us. Good job, us. Questions? Oh yeah, sorry, awkward. Can't actually answer them. Okay, so we've got one more here. So I'm going to make it as hard as I possibly can, because again, I know you guys love being challenged. Sorry, that one was actually me snorting and laughing because you guys don't like being challenged. So let's see, I'm trying to think of the hardest possible sequence that I can come up with. So I tend to screw these up, so if I make a mistake, I'm going to blame someone else. let's see. I'm going to go with 9 over... There we go. I like this one. So I'm not going to talk because I'm going to try to make this actually work out really nicely. Okay, let's see. Does this work? Hope you're not copying it down quite yet. You gotta have a little less faith in me. Yep, I screwed it up. Told you. No one. I called it. Called it. There we go. There is our third sequence. 9 over 14, 3 over 2, 7 over 2, 49 over 6, ellipses. So, you're looking at this going, I hated fractions before, now I'm like super hating fractions. Like, what am I supposed to do with this? Well, in this case, like what's happening is this is definitely a geometric pattern, or at least I'm crossing my fingers that this is definitely a geometric pattern. What's kind of hard is like you see a lot of changes. Like there's not really a consistent multiplying by like we could get with this one afterwards. There's a lot of simplifying that's happening with these fractions. So instead I'm going to trust that doing this a sub 2 divided by a sub 1 thing is going to work out for me. Okay, so a sub 2 divided by a sub 1. So order is really important here. So a sub 2 is 3/2 divided by a sub 1. Because again, we want to figure out what the ratio is so we can see what's being multiplied. That's going to be equal to... Take sec 1 and reciprocalize it. Patent pending, that word does not exist yet. This is going to give us 42 over 18, which simplifies if we divide top and bottom by 6, down to 7 over 3. So it would appear that our common ratio is potentially 7 over 3. So if you're a trusting sort of person and you don't, and you figure I haven't made any mistakes here, you're welcome to go ahead and jump right in and just go ahead and say that r is equal to 7 over 3. But if not, we can again make that little test. So over here, if we multiply times 7 over 3, let's see what happens. So times 7 over 3, that's going to give us 63 over 42. Not quite the same thing, but if we divide by 21, 63 over 42 does become 3 over 2. If we multiply this guy times 7 over 3, you can almost see it happening. 21 over 6, divide by 3, we get 7 over 2. And then this one, finally, the pattern really becomes clear. It's like all that other stuff is kind of canceled out. 7 over 2 times 7 over 3 is 49 over 6, which is what we have. So in fact, it does appear that r is equal to 7 over 3. So, Mr. Steele, will we get problems like that are rude and evil? Yes, you will get problems like that. Like, in fact, there's nothing wrong with that. In fact, I really like writing those ones because you feel really clever when you get them right. Now, will you have problems where there are probably mistakes because I was trying to get a really clever, cool-looking ratio? Yeah, you'll probably get some of those. So I might have even made a mistake while I was making this video and used the power of editing to fix it. So again, common ratio, very important part of any sequence. If we want to be able to write the rule, we need to find that common ratio. And we just did 3 times. So moving forward, now that we found the common ratio, let's do a couple times. We're not going to do a whole lot of examples of this because, I'm already tired of making the video. But let's make a couple things here. Let's practice the real skill that we want, which is being able to write a rule and finding any term from that rule. So for this next part, we're going to do like the first, big kind of problem. Write the rule, find the 10th term. Pretty standard thing. Like you might ask, why aren't we finding like the 400th term of the sequence? Well, you'll see pretty quickly in just a few minutes why that would be a bad idea. So, where we're going to start is we are going to begin our first write the rule and find the term with this sequence, which I allege is geometric. No mistakes. Crossing my fingers. So 8, 12, 18, 27. So again, your mind might immediately gravitate towards arithmetic, but of course we can see this is an arithmetic. We had 4, then we had 6, then we had 9. Those aren't all the same numbers, at least in my universe. So it appears that in fact we do have some sort of different sequence. So let's go through and actually do this the nice way. Let's be really formal and careful here. So let's start by finding r. So what is my ratio? Because I'm assuming you can find a sub 1. Oh look, there it is, there's a sub 1. Not hard to find. R, though, a little bit harder. So let's do this. We need the second term divided by the first term. And the reason I'm going here is because I don't recognize this multiplication pattern just right yet. What numbers multiply 8, or what do you multiply 8 by to get 12? What do you multiply 12 by to get 18? It's not jumping out at me. It's probably some sort of fraction. And, you know, we don't love fractions all that often here. We make them sad, send them to therapy. It's really sad. So here we go. R equals 12 over 8, because that's a sub 2 divided by a sub 1. 12 over 8, if we divide both top and bottom by 4, is going to give us 3 over 2. So I'm going to go ahead and posit that our ratio is 3 over 2. If you don't believe me, you could also check 18 over 12. We'll just do one more to check it. 18 over 12 divided by 6, we get 3 over 2 also. So I'm going to go ahead and say that I trust R is 3 over 2. So that's great. If we want to write the rule, it's not hard now. We just need the first term and R. We found R, it was right here, and we found a sub 1 because it was the first number on the list. So our rule, in this case, and I think on your homework I actually give you a line for the rule. Our rule is going to be a sub n. Always need a sub n because we're trying to find a rule for the general term. It's going to be equal to a sub 1 times R to the n minus 1 power. So just like with arithmetic sequences, our rule has an n in it because we want to be able to plug in an n for whatever term that we actually want. So lovely, we found our rule. Now we're going to use said rule to find the 10th term in the sequence, also known as a sub 10. So okay, should not be too bad, just going to be kind of ugly. So what is a sub 10 equal to? Well, it's equal to the same stuff. Start at 8. We'd multiply by 3 over 2 over and over again, but we do it to the 10 minus 1 power, because again, now 10 is taking the role of n. So okay, so what does that equal to? Well, that's 8 times 3 over 2 to the 9th power. And now a lot of people immediately want to go, oh, well, what's 8 times 3 over 2? But you can't do that because the order of operations say we have to do exponents first. So we actually have to do this guy, this 3 over 2 to the 9th, first. And who do you blame for that? You blame Senor PEMDAS. It's PEMDAS's fault. So we've got to do that first. So what is this equal to? Well, you know what's funny is I don't even know what 3 to the 9th power is. I just didn't pay attention to that. So I'm going to go ask my calculator. Calculator? Yes, master. What is 3 to the 9th power? Computing, master. It appears that 3 to the 9th power is the lovely 19,683. So 19,683 is 3 to the 9th power. I mean, who knew? And then down here, we've also got 2 to the 9th. So now, before I go on, and again, what I'm doing here is I'm just trying to get it as a fraction. In reality, you guys are probably just going to punch in your calculator and get a decimal. It's actually okay in this case, but I'd rather be careful. So in this case, now I want to know what is 2 to the 9th power. So I'll make the calculator do it this time. The calculator's quiet. He seems embarrassed or something. So as it turns out, we get 19,683 over 512. And this is all being multiplied times 8. So lovely. What is that going to end up being? Well, again, let's just make the calculator do the work for us. It's always fun to have the calculator do heavy lifting. So we just multiply straight across. It's 8 over 1, so 8 times 19,683. That's going to be divided by 512. And our term is going to be the lovely 307. It looked like 54. Didn't memorize it. 546875. And oh boy, we got our term. There's the 10th term. It's some decimal. Yuck, I don't like decimals either. Well, who do you like? Jeez. Well, of course, you don't want to do that. Like, you can do it and get a formal answer, like get a nice exact one, although this is an exact number, like one that's written as a fraction, a little bit better. And you could do that by simplifying with the 8 and the 512, because this fraction actually does simplify. The reason is 8 is 2 to the 3rd, so I'm just going to kind of write it right here. You don't have to do this all the time. I'm not expecting you to do this. 19,683 is fine. Nothing's going to simplify with that guy. It was 3 to the 9th. Down here, 512, we got by doing 2 to the 9th power. So in reality, we actually have this thing to deal with. 2 to the 3rd times that over 2 to the 9th. Well, that 2 to the 3rd over 2 to the 9th can actually simplify. Like, we can end up with the powers simplifying to just 2 to the 6th on the bottom. in which case we could actually write this guy, this 307 thingy, as 19,683 over 2 to the 6th, and 2 to the 6th is 64. Notice now, if I pull up the calculator and force it against its will to calculate 19,683 divided by 64, bam, same answer. So if you want to be everyone's favorite student, you want to make it a fraction. So this is better. Like, I would prefer this fraction-y one. It's definitely better. But again, you don't have to. And if you want to do it, all you have to do is kind of use the exponent rules to simplify stuff beforehand. So lovely. We wrote the rule and we found a sub 10. Write in the rule, easy. Finding a sub 10, easy if you just punch in the calculator. Not so easy if you want to be careful about it and write it with its fraction. So okay, we did one. Let's do a second one. Let's go with, trying to think of a good one here. Oh man, I don't want to use that one. I see another one sitting here on my paper as I look at my notes. I'm going, that's a stupid one. It has the same ratio as the one we just did. Like, why would I want to do that? So let's instead do this one. Let's go. Ooh, no, I got it. Let's go that. Yeah, that's cool. That's nice. Let's go with that one. Yep, look at that. Now it's getting creepy. Look at that. There is our second sequence that we're going to write the rule for. So we got it there. Now, for this guy, what you can kind of assume as we start off is that, you know, I've given you a geometric sequence, because otherwise that'd be a jerk thing to do. Like, hey, find the rule, find the rule. Oh, you can't because it's not geometric. Actually, I might do that, but I'm not doing it this time. So looking at this guy, you might go, okay, well, what am I doing to get from here to here? Like over here, we can kind of see it. It looks like we're multiplying by -4. Over on these guys, though, not so obvious. So let's just check it really fast. Not that you always have to do this. If it's obvious, go for it. But for the ratio, we take the second term and we divide by the first term. That's the same thing as 1/2 times -8 over 1, which would be -8 over 2, which is -4. So I'm going to go ahead and say that, yeah, looks like my ratio is -4. So very cool. Why is that nice? Well, I can go ahead and jump in to rule mode really quickly now. So what is my rule? My rule will be a sub n equals my first term times my ratio to the n-1 power. At that point, my rule is complete. I got it. It's there. There it is. So great, we wrote our rule. Why do we want a rule? Well, because rules allow us to calculate individual terms. So if I want a sub 10, I'm just going to plug in 10 for n. -1/8 times -4 to the 10-1 power. Same thing as -1/8 times -4 to the 9th. So in this guy, I'm just going to go right to the calculator. Now my calculator stinks, so because I'm just using the one from the computer, but I'm going to go in here and actually type it in a really weird way. I'm going to start with -4, so -4 to the 9th power, because again I have to do that exponent first. It says -4 to the 9th power is -262,144, so -262,144, and that is being multiplied by -1/8. So according to the calculator, if I multiply by -1/8, so divide by, I get as my answer the lovely old 32768. And so now we can kind of ask ourselves, does that make sense? Is that good? Well, one, it's already a nice whole number, so we don't even have to worry about the fraction-y stuff we did before. And second, like, we can kind of ask ourselves, well, should the answer be positive? Because it is alternating. Well, if you look, we're looking for the 10th term. The first term's positive, the first term's negative, second one's positive. Third term is negative, fourth term's positive. Looks like all the even terms are positive, so a sub 10, which is even, should be positive also. Hey, look, it's positive. Looks like we did the right thing. I'm going to go ahead and check it off with a smiley face and assume that I did. So, good job, us. Pat yourself on the back. Unless you can't reach your back, in which case you can have a friend pat you on the back. So there we go. We wrote the rule. We used the rule to find a sub 10. Nothing really different here. We just have a different rule and a different kind of pattern we're looking at. So now it's multiplying patterns. Lovely. So what else do we have? We've just got one more skill to kind of do with this guy. Same exact kind of question, just going to be different information that you're given. Alrighty, home stretch here. We're ready to get going. We want to finish this off and look at, getting the last little twist that we're going to have today when it comes to these geometric sequences. So far, we've calculated a common ratio. Well, first of all, we talked about all sorts of stuff, did all sorts of great stuff. Then we just practiced finding the common ratio, that really important thing that describes how it's being multiplied over and over again. And then we wrote the rule and found a sub 10, found a term by doing that same kind of stuff. Now we're going to do the same thing. It's just going to be different information that we're given. Instead of seeing the whole sequence laid out beautifully for us in all its splendid glory, instead we're going to be given some information, just like we did in the last ones. Tomorrow we'll handle when you're given two random terms. Like there's this cool little trick that I call Molina's rule that we'll use. But for today, we're just going to be given two pieces of information. We're going to get a specific term of the sequence. And again, you can assume they're geometric for today. So we'll get a specific term such that we have a situation like this. So they're telling us a sub 5, the fifth term, is 96. And they're going to tell us the ratio. So they'll save us the trouble of having to figure out what that R value actually is. So here we go. A sub 5 is 96 and R equals 2. What you mean just 2? I say it every time it comes to mind. I've watched Charlie and the Chocolate Factory too many times. So anyway, here we go. We're looking at this guy. We're going, okay, the fifth term's 96. R is 2. Well, I mean, we could probably go backwards and just figure out what a sub 1 is from there and write the rule. And we could probably just multiply by 2 a bunch of times and get 10. Of course, with situations not going to always be so pretty. So instead, let's go through this one formally and make sure we know how to do this. So if you remember what we did the last time, a good place to start is with our general rule. Because again, we're trying to write the rule, so we need to use the rule. Well, for a geometric sequence, a sub n is given by a sub 1 times r to the n minus 1 power. So that's important. That's where we're going to start. So the question might be, well, what do we already know about this a sub n? Well, first of all, they told us that r was 2. So if we use the fact that r is 2, we can actually simplify this guy already a little bit right off the bat. This specific geometric sequence is going to be given by a sub 1 times 2 to the n minus 1, because as it says right here, r is 2. Now, what else we know? Well, if we think about it, we also know some information about a specific term in this sequence. Like we know a sub 5. The fifth term is 96. So we can actually go in here and simplify it a little bit using this piece of information over here. In fact, I'm going to highlight that, change its color to emphasize it a little bit. I think I don't do that enough. And pretty colors are always nice. So if we know a sub 5 is 96, that means that we know n should be 5. So both here and here, n is 5. And then also, since we have a sub 5, that whole thing is equal to 96. Meaning that we have this equation that we're going to look at. A sub 1 times 2 to the 5 minus 1 power is equal to 96. So if we can just solve this guy for a sub 1, we should in fact have all the information we need to write the rule. And then of course just plug in and run from there. So from this guy, we've got now 2 to the 5 minus 1 power is 2 to the 4th. That's 16. So a sub 1 times 16 equals 96. And then if I just divide both sides by 16, I'm going to get that a sub 1 is equal to 96 over 16, which is equal to, computing, 6. So a sub 1 for this sequence is equal to 6. So this guy, the sequence where a sub 5 is 96 and r is 2, that guy can be described by a sub 1 n equals a sub 1, which we just discovered to be 6, times 2 to the n minus 1 power. So we've got our rule. There it is. So lovely. We got the rule. Why did we want the rule? Well, of course, we wanted to figure out what was a sub 10. Like, we just want to know what the 10th term is. So, okay, a sub 10 is equal to a sub 1 times r to the 10 minus 1. That's the same thing as 6 times 2 to the 9th power. Remember, we have to do this guy first. So, in my calculator, we do 2 to the 9th. That's equal to 512. We multiply it by 6. And we get 3072. So our rule was this guy, found it right up here, and our 10th term, the one we were looking for, term number 10, 10th number in this list, is 3072. So we got those things. All we had to do basically was use the rule and fill in the rule. So we basically fill in the general rule. So that's all we're doing, just like we did with arithmetic. Like if I could, I would have just stuck like a arithmetic example on the right side, but that would have been confusing. So lovely, we did it once. Let's just do it again. This time let's probably use a fraction one, because people are just so bothered by fractions. So let's make sure here. So give me a number. Let's see. George will probably say 9. Damien will say 3. Everyone else will say nothing, and just laugh at the humor of listening to them both yell at the same number every time. Someone will say 42, and someone will probably say 1. Nikki would probably say 1, because she always thinks that's funny. So let's go with, I don't know, let's go with a sub 7 equals, let's go a nice number, 42. And then let's also say that r equals 1/3. So, already got the fraction. Couldn't keep them away, could I? So what I'm going to do is I'm going to change colors here, just because it'll probably help us a little bit if we emphasize the color pieces a little bit more. So we got that guy is red, this guy is blue, and now our rule, as it says right here, is a green. So what are we going to do here? Well, you can probably figure it out. You can probably jump ahead of me as I do this. That's cool. I can't see you anyway, so you can really do what you want with the problem. But okay, so what are we going to do? Well, we're going to start by filling in the rule, because this is our general rule. So what do I know? Well, first, I'm going to use the blue fact that r is equal to 1/3. If r is 1/3, then r is 1/3. Like there it is, we plugged it in. Next, I'm going to take that information and I plug in the red stuff that tells us about a specific term. Because again, what we're trying to do is we're trying to find a way, a quick path to get a sub 1, because we can't see that right now because we only know the 7th term. So from here, a sub n is going to be 7, or a sub 7 is our term, so n is 7 in both cases, as it says now, and a sub 7 is 42, so I'm going to set that whole thing equal to 42. So there it is, lovely. What does that do for us? Well, now we have an equation right here that's all in one variable. We just have to find a sub 1. So I just need to simplify this and then actually solve it. Well, I've got a sub 1 times 1/3 to the 6th power. That was bad speaking. It's all equal to 42. So now, I don't know what this thing is. 1/3 to the 6th power. So I do know, though, that it's going to be 1 to the 6th over 3 to the 6th. So 3 to the 6th, 729. So this guy is a sub 1 times 1 over 729. And it's all equal to 42. So okay, now what I want to do is I want to figure out what's a sub 1. Like, what is that first term in the sequence? So to solve this guy, I could divide by 1 over 729, but that just looks ugly. Instead, I'm going to multiply both sides by 729. Why not? The reason being, that'll cancel this guy, and I'll get a sub 1 is equal to probably a pretty big number, 729 times 42, 30,618. So we got a big number. You're going to notice that happens a lot with these geometric sequences and later series. You get big numbers a lot of the time. So what is this guy? This guy is good old A1. So our rule for this particular problem is given by a sub n equals a sub 1, which was big, times my ratio to the n minus 1. That looks like a lightning bolt, so it's kind of cool. There we go. That guy. So there's my rule. Remember, we only want rules defined to specific terms. So a sub 10, what shalleth be that? Well, changing my colors just for kicks. A sub 10 will be 30,618 times 1/3 to the 10 minus 1 power, which is 9th, so 9th power. I don't know what 3 to the 9th is. This thing's probably not going to work out really nicely. So let's see here. So I want to do this, 30,618. Going to divide by 3 to the 9th. I get this thing look like 1 point, a lot of 5s. So a sub 10 is equal to 1.555. You can probably figure it out from there. You know, we'll go with 3 decimal places for now. I'll put some dot dot dots just to remind myself that's not exact. And of course, yeah, that's great. You know, do I really want this thing in exact form? Well, yeah, I do. So you could probably use your calculator. You might be able to get away with it. But if not, if we think back to what we had here, this whole thing, like, so yes, like, I don't mean to obscure it. Like, that would be our answer for a sub 10. I just want the exact one. Well, this was 42 times 729, which is 42 times 3 to the 6th. We're now multiplying by 1 over 3 to the 9th. So imagine what we did before. 3 to the 6th cancels, that leaves us 3 to the 3rd. This appears to be equal to 42 over 27, which I submit is a lot prettier than this thing with the ellipses in there. Leave the ellipses to the English teachers. So there we go. Of course, what I want to do is I want to just make sure, did that actually work? So is 42 over 27 1.55? Yes, it is. So it looks like we got our right answer. So we found our rule. There it is. And we found our term. There it is. So nice job, everybody. We have done everything we need to for this geometric sequences thing. So let's go back here and take a look at what we did. To start off this, does not want to help me. To start off this lesson, we started by talking about this not really new kind of pattern, but this other kind of pattern that's pretty fundamental and useful, called a geometric sequence. It's where you multiply the same thing over and over again. We talked about how it could develop and how you could see where this rule came from, and found out the rule was a sub n equals the first term times r, that ratio, that thing we multiplied by, to the n minus 1 power. We went through and found the common ratio a couple times to practice that. We wrote the rule and found a specific term when we were given the entire sequence, when we were given the sequence to start with. And then we did the same exact thing, except when we were given a specific term and a ratio. And as I said earlier, we're going to wait till tomorrow to do it when we have 2 specific terms, because there's this cool little trick that we can use for that. So at this point, I'm going to go ahead and say I'm done. The rest of this period, you can work on the homework assignment that's coming out to you in just a second from Ms. Weinstock. So without further ado, this is Mr. Steele, signing off for the day. Have a good one. Bye.